we'll move on to our next topic. So, Ivan, can you turn on your video and start sharing your screen? So we're going to look at effect of variable scope work packages and batching on project contingencies. So Ivan Damjanovic is a professor and director of engineering project management at Texas A&M. He's our PPI partner for delivery of some education that we'll talk about at the end of the day. Ivan specializes in qualitative and quantitative methods for management of engineering and project risks, as well as management of infrastructure and transportation systems. He has an extensive experience in engineering risk and safety analysis applied to projects from different industry segments, including transportation, oil and gas, and technology development. So I'll turn it over to you.
Well, thank you, Gary. Let me try to share the screen. Okay.
Okay, we got it.
Okay.
Yeah, we're good. We can see your screen.
Very good. Okay, excellent. Okay, my name is Ivan Damjanovic. I'm a professor at Texas A&M University, and this is the work I've been doing with Kayla Butcher. She is our PhD student. Today's topic is about the variable scope work packages. I know the title sounds a little too long, but basically what we are trying to do here is look into the effect of work packages that are flowing through the production system that are not on equal sizes, okay? And we are particularly interested in contingencies and risk measures. So I'll give you a little bit of a brief overview of project risk management, and in general, dividing project risk into two major categories. And this is where the discussion about variability versus uncertainty comes in. So we typically classify risk into two different categories. First one being incremental, or what we call as a low impact, high frequency sort of risks. Another term for that is additive risks. These are the thousands, if not tens and hundreds of thousands events that can happen on a project. They are small, they convolve, and overall they cause what we refer to as a variability. So these incremental or additive risks are also referred to as variability. We don't identify those events specifically, each one independently. However, we lump them all together because their impact is really small. Occurrence is fairly frequent. The second type is what commonly gets referred to as risk. Those are higher impact, low frequency events. Those are the events that we actually identify, and we go through the process of identifying and then quantifying their impact. These two are generally managed separately. Incremental or risks or additive risk or variability is typically handled through a contingency, whereas high impact, low frequency events are typically done through the risk register by first deciding what you're going to do with it, whether you're going to transfer it, mitigate, and finally accept them. Okay, so this topic deals with this presentation deals with both aspects of risk management, figuring out contingency as well as understanding what production metrics tells us about specific risks. So project incremental risk and referred to as variability can come from multiple sources, but if we look at queuing networks and production systems in general, we have variability that is rooted in a process or crew production variability. Given the same scope of work packages, things will get done slightly longer or shorter depending on these thousands and thousands of the events that contribute to this variability. And we also have arrival variability that is affected by production variability of tasks or the processes that are ahead of the the production process we are considering. So basically, we have typically production variability or process variability and the arrival variability. Now, in the actual production system, when we add this variable scope sort of work packages, so what do I mean by that? Work package can be defined, it can be very small and go through the same production system, or slightly larger and go through the same production system. As they are being released, they are a variable scope. What that creates is a correlation between the arrival time and processing time, okay? What do I mean by that? Well, the larger work packages will arrive at a slower rate because the upstream processes are processing those longer. And then, as they arrive at slower rate, it will also take longer to process them, okay? Because there is a lot of things to be done on this larger work package, and vice versa. If we have a smaller work package, it will flow faster through the system, and it will, arriving to the process that we are considering, it will take a shorter period of time. So that is that correlation. The larger work packages and the smaller work packages, as they flow through the network, create correlation between the arrival time and processing time, or arrival rate and processing rate. So we hear this often in terms of improvement and in terms of discussion, how much of that variability actually impacts. Should we standardize in some way work packages or not? So that's the first thing a lot of times comes into people's mind as they try to reduce the variability. Okay, so what is the impact of such variability on production metrics such as cycle time, working process, completion time, and the respective contingency? And what strategies project managers can use to reduce its impact? So that was the motivation of this work that Kayla and I have been working on the last 6 months. So in order to contrast and compare, we have introduced 5 different cases. So the case A is your standard MM1 queuing network. Okay, so we have variability with the arrival rate that's coming out of the stock over here, or source over there, and flowing through the production unit with its own variability, and it goes into sinks or another stock. So only arrival and process variability. We are dealing with the same scope of work packages. Now, case B is what typically happens. So here we illustrate only 2 different sizes of work packages. You can imagine that this could be multiple different ones depending on the size of the work packages. But basically, you have arrival and processing variability with different scope of work packages, okay? So we have arrival, certain smaller work items are arriving faster, okay? And they are being processed faster, whereas the arrival of slower ones that are bigger takes longer to be processed. So arrival and processing time is correlated. Now, case C and case D that we introduced are a variants of this. Basically, what we try to do here is see if we have buffers, what kind of impact the buffers can have on the variability of the downstream production matrices. So KC is when the arrival and processing variability have a different processing time but the same arrival time. So basically, somebody is sending work packages with the same rate, with the same average rate, regardless if they're big or small. So this is an example, let's say the beginning of the production system, they may just release at the same average rate work packages, or it could be somewhere in the middle of the production process when somebody buffers everything and then again releases that. So that's your KC. Case D is inverse of that. Arrival and processing variability with a different arrival time, but then the same average processing time. So this is where arrival comes into, and arrival is impacted by scope variability and comes into the following process, regardless of the scope of the previous one. This is typically when we have a situation when the different work packages towards the end of the production pretty much kind of it will require the same amount of time regardless of the size. So that's the case D. And then we have a proposal for one management strategy is where we process the fast one first and the slower second. Okay, so we segregate them into different sizes and then we process them in that order. Okay, it doesn't matter really if it's first slow or first fast, but we don't mix them together. So that is a case E that we wanted to see what would be the potential impact. Now, some of these have a closed form solution, some of them not. It gets really complicated because we are departing from MM1 type of queue system into basically general type of queuing networks. And there are potential way of dealing with this theoretically as well as with the simulation. We wanted to just have a sense of what is the actual impact here. So how do we measure the work package scope variability? Well, we keep the same averages, same expectations. So if you look at this table, slow, fast, this is your arrival rates, and these are your processing rate. Regardless of how I set it up, slow versus fast, if you look at the expectation of arrival rate is always 2.5, and the processing rate is always on average 5. Okay, we wanted to keep this way because we assume that they have the same expected amount of time rate, but we wanted to show how variability in the processing time and the arrival rate will actually impact some of those production matrices. So high scope variability here. We have 0.5 arrival rate that is matched with 1 of the processing rate, and 4.5 fast rate matched with arrival rate matched with the processing time of 9. So again, the expectation of arrival rate is 2.5 and expected production rate is 5. Note that our utilization is 50% here. So that's a higher scope variability because you see the contrast of 0.5 to 4.5. This will be a lower scope variability. Ultimately, we can get to a case when it's both slow and fast at 2.5. These are, by the way we scale them is we are equally likely. So that's why the averages are like that. So 2.5 and 5. So max range divided by the range would be now intensity of the work package scope variability. So the higher this is, actually, the more it converges towards 1, we are getting an extreme variability. Okay. Now, what are some results here? Okay. So I want to point out this one, it relates to our time to nth arrival or project completion time. So if you need to process 1,000 work packages, how long it's going to take you to process 1,000 work packages? So note that my case A, this is A, standard case A, is actually, should be, you don't see it here well, but it's a flat line here. Okay. Now B is the case which represents more realistic case, and note what happens to our completion time. It just grows. It grows together with increase in scope, work package scope variability. So the more variability I have in the work packages, the higher my mean completion time. This is actually the case because I have separated those arrival rates. Now I have arrival rate that is an extreme arrival rate of 0.5 and another extreme of that is 4.5. So this is an important implication here that even without necessarily setting up contingency here, I have an impact on even my mean. So contingency, we set up some form of a confidence interval. Now I'm actually having an increase even in a mean value. So this is an interesting result, I would say, because we often underestimate project duration. And this could be part of why we actually do that. We are consistently over our estimate, which indicates that our mean actually shifted, not just our variance. And our variance increased as well. So you can see the same sort of trend here. As we increase the variance of work packages, and you can see that as a max range divided by the range going from 0.2 to 1 here. Note that as we reduce this to 0, they all will converge to the same number here, because we don't have any variability in scope. Okay. Here is the WIP. Actually, that's another interesting result here is the WIP, impact of WIP on this variable package, variable scope work packages. It is so significant on the KC. And that really makes sense. We spend a lot of time analyzing this. It makes sense as we are actually increasing variability in our processing time and feeding with the same rate. It explodes with the queue explodes, and cycle time explodes, as well as the work in process. So we should be very careful about variable scope work packages from the perspective of process. Now we changed and looked into different sorts of utilization. There was no significant impact of different utilization rate. Of course, utilization will cause project to higher utilization will have lower completion time, but we have what you see the results here are standardized with a case A, which is baseline case. So there is nothing particularly let's say our situation is not particularly sensitive to the utilization of the server. Okay, we wanted to check if there are some sort of nonlinearities in the completion time, but this kind of this case showed us that there were nothing significantly happening from the perspective of project completion time. Now, from the perspective of cycle time, and this is the case B and C, what you see, it is sensitive. So the higher utilization you have, okay, the impact of variable scope, but the variable scope work packages increases. So we should be very careful when we deal with a situation where our work packages are of different size and we have higher utilization. That's what these figures show. Now, interesting was the case for E. Basically, utilization really didn't matter on the work process here in the cycle time as well. So because basically we are processing one, and then the one type of work packages, and that when that is done, we are processing another type of work packages. So that actually has some benefits with respect to some of the matrices such as working process and cycle time. Okay, so some of the findings here. So average completion time is sensitive or governed by the upstream work package scope variability. Impact could be significant and all the way to 150% of the initial estimates, such was the cases in B and D. Of course, this is an extreme case. So we should be careful about developing our production system and setting up our production system, because such setup actually can cause a need for higher contingency. The results show that the variance of completion time is also impacted, which reflects a more realistic modeling of production should include scope variance and scope variability. The production performance indicators that are most sensitive to work package scope variability are cycle time and working process, and this was particularly the case for when we have an average arrival rate with a variable production rate. So it was pretty dramatic in that sense. Management strategies that separate large from small work packages performs equal to the real case from the perspective of completion time and its distribution, but significantly outperforms case B from the perspective of the cycle time and working process. So that's one interesting finding we got there. The results show also that the higher utilization rates in general amplify the impact on the performance metrics such as the working process and the cycle time. However, the impact is negligible for case E, which is our management strategy where we segregate different work packages types and then process them sequentially. Some recommendations here: consider production modeling and scope variability to find and manage needed contingency. I would also say that this needs to be that work package, the working process and the cycle time has to be part of the risk register and be managed that way, because the risk of rework is directly proportional to amount of working process you have. So that's one aspect. And the second aspect is that contingency, as we talked about before, even the mean can be shifted and the variance dramatically increases. Consider making less variable scope work packages, only if it makes sense, again, from the project management and sequencing viewpoint. Sometimes it doesn't make any sense to separate them or make them smaller variability, because that's how the project is typically executed. But what our study shows is that you ought to consider it. Process small and then large work packages or vice versa. This breaks down the variability and allows for reducing working process and cycle time. Project duration remains also sensitive to work scope variability, even for this case E, but it doesn't exceed, which is a good news. If you're considering buffer to eliminate upstream variability, that's not always a good idea, as you saw in the case C, especially if the following work is then again segregated and impacted based on the size of the work package. So be very careful about that. Consider adjusting the arrival rates to match the average inter-arrival times to start with. This is something that will help, at least from the point of having the same sort of completion time. The mean of the completion time will not be amplified if you have that, but still increasing variability of the work packages will have impact on other measures such as working process as well as the cycle time. With that, I'm open for any questions, comments, suggestions, and so forth.
Very interesting, Ivan. Thank you for sharing that.
Sure.
Okay, audience, come on. Got to kick in some questions. I know we got you in the deep end here, but we always chunk the work. We're always creating work packages. You've given us some really good insight on the cause and effect relationships of how we had designed those work package, how we managed the flow of those work packages
Mhm.
and results. That's really good stuff. I'll start with a question while we wait for the person to ask something. In your study, did you, maybe you didn't need to go there, but did you quantify how did you define a work package? Was it based on a quantity basis? Was it an hour basis, or did it not matter?
The way we define it is we assume that the larger work packages take longer. So it didn't really matter for us in terms of like defining it actual hours. We use those hours in terms of, let's say, the smaller work packages will be produced at will be arriving at the 0.5 rate of arrival, whereas the larger work package, the larger work packages will be having slower arrivals, and the smaller work packages will have a faster arrival, which was 4.5 in this case. We wanted to keep the average of 2.5 because average was what we typically consider. We don't separate them. So in this study we try to separate them and see what the impact of real situation is, because we often say, it's just 2.5 arrival, but this extreme variability can result in a lot of bad things to our project from the risk management perspective.
I'm with you, man. Before we started using production control, we had wide range of scope inside each work package. It was like little to ginormous, and we just had chaos. That's really what we had, was chaos.
Yeah, another thing what I point out here that might be quite useful is that that this kind of study illustrates that that we really need to think about production system earlier, even during the very early stages of identifying and managing risks. So I think a good way of bringing up this to attention of the decision makers is to say that, hey, how we define production system, you may need this much of a contingency or that much of a contingency. Okay, and that is the bottom line when a project goes through a stage gate process and things get budgeted. And I think, I mean, this study shows that the contingencies can be significantly impacted.
I believe it. Yeah, we got a question for you here. Can you please comment on the implications of decisions on the transfer batch and or process batch of the work package on your research?
Good point. So this was initially part of the scope we're gonna do, but we ran out of time. So we have looked into the batching, and the batching from the perspective of we have seen some effects of the batching, but I couldn't claim one thing or another in terms of the actual impact. So next study we plan to expand on this with the batching as well.
Okay. Another question: what would happen if this analysis was used on schedule, activity, scope, and duration?
I think that's the way to go. If I think bringing up the impact of setting up a different production system on the schedule, it's the way to go, because ultimately we are defining contingency on schedule. We are not defining or cost, but we are not defining on in a production system. So now the thing is that you won't be able, the repercussion of this is ultimately that you won't be able even to have a proper estimate of a contingency if you don't understand the production system. And that's where a lot of our, in my viewpoint, a lot of our mistakes as a general practice, I mean, are made because we use a method that doesn't necessarily allow you to see the whole picture. So adding the production system analysis into scheduling is is essential for better understanding of the contingency and ultimately of how a project goes through the phase gates and the economics of the project.
Well, and how to dial in the production system to operate more effectively so you get more
Yes.
and faster. Yeah.
Yeah, and in that viewpoint, Gary, I would say that that's the sound project risk management practices.
Yeah.
It's your monitoring risks and responding to risk, and you ought to know something about production system if you want to manage risk associated with production. So,
And production is where it happens. That's where the
yes.
Okay. Well, very good. Thank you, Ivan, for sharing that. And I guess Kayla wasn't able to join us.
Kayla might have been able. I'm not quite sure. She was traveling, but I hope she made it. And I would like to thank again her for taking a lead on this and putting a lot of work into it.
Yeah, just so the audience knows, Kayla is the graduate student that's been doing all the work here. Ivan's the messenger. So pass our thanks on to her as well.
Thank you.
All right. Thank you.
Thanks.